Imagine floating effortlessly above Earth, gliding through your cabin with no weight to hold you down. It sounds like freedom, even fun. But there's a hidden cost to living in microgravity. Our bodies are built for life on a planet with gravity, and without it, everything from bones to muscle starts to change. In space, the pull that once kept us grounded is gone, revealing just how much our physiology depends on this invisible force. Let's explore why astronauts lose bone density and what it tells us about the power of gravity. Fact 1. What is gravity? Have you ever dropped your phone, hopefully not on purpose, and watched it tumble straight to the floor? That invisible pull bringing it down is gravity. At first glance, it seems simple. Things fall, but gravity is much more than that. It's the force that keeps you firmly on the ground, ensures the moon stays in orbit around Earth, and governs the intricate dance of planets around the sun. It's the quiet rulebook of the universe. Think of gravity as an invisible hand connecting every object with every other object. The bigger the object, the stronger the pull. Earth is massive, so its hand is strong enough for us to notice every day. But even tiny objects, like your coffee mug, tug on the Earth, although in a way so minuscule we can't detect it. Gravity operates constantly, shaping our world in ways we rarely stop to consider. Oceans stay in their basins, rivers flow downhill, and we remain firmly planted on solid ground, all thanks to this ever-present force. Gravity doesn't pick favourites. It acts on planets, stars, dust particles, and even light. Though light behaves in strange ways under gravity's influence, a story we'll get to later. It organises the chaos of the cosmos, turning randomness into order. Without gravity, objects would float freely, planetary orbits would collapse, and galaxies would unravel. Gravity isn't flashy, but it's the invisible artist painting the universe's masterpiece. Even more fascinating is how gravity connects the very large with the very small. From microscopic particles to massive black holes, nothing escapes its influence. It determines the life cycles of stars, the formation of planets, and the paths of comets. Without it, the universe would be an unbound, chaotic space of drifting matter. Gravity quietly weaves everything together, reminding us that even forces we cannot see or touch shape the very nature of reality. Fact 2. How Isaac Newton discovered gravity. Isaac Newton is often imagined under an apple tree, hair wild and notebook open, staring at the sky. The story goes that he watched an apple fall and wondered why objects always fall straight down. While the exact details are partly legendary, the essence captures his brilliance. Curiosity sparked by a simple observation. Newton realized that the force pulling an apple to the ground must also guide the moon around Earth. Suddenly the same rules applied both on Earth and across the cosmos. Before him, celestial motion was seen as mysterious, entirely separate from earthly physics. Newton's insight bridged the gap, revealing a universal force connecting all matter. By observing motion carefully, performing calculations, and thinking boldly, Newton discovered that gravity was not just a local phenomenon, it was universal. His work laid the foundation for centuries of physics, creating a framework that allowed humans to predict planetary motion, calculate trajectories, and eventually explore space. Newton's moment of wonder beneath the apple tree wasn't just about fruit, it was about curiosity, pattern recognition, and seeing connections where others saw only mystery. Even today, Newton's legacy guides scientists and engineers. His laws are applied in everything from launching satellites to predicting asteroid paths. By asking why at the right moment, Newton taught us that understanding nature starts with observation, imagination, and a willingness to see the invisible forces at work. Fact 3. The falling apple, myth and meaning. The falling apple story is one of science's most famous legends. Did it really hit Newton on the head? Maybe, maybe not. The significance isn't the apple itself, it's the curiosity it sparked. Why do objects fall? Why doesn't the moon crash into Earth? That simple question transformed science forever. The apple symbolizes human curiosity. Newton's question reminds us that even ordinary events can hide extraordinary insights. When we drop something and catch it just in time, we're participating in the same natural phenomena that inspired groundbreaking discoveries. The story is a testament to how noticing small details, An apple falling, a coin rolling can lead to monumental leaps in understanding. It also captures the essence of scientific thinking, observation, questioning, and connecting the mundane to the universal. Every falling apple is a tiny experiment, illustrating gravity's pull and the natural order of things. The legend persists because it embodies the spark of insight that propels humans to explore, experiment, and learn. Gravity may seem simple, but it is deeply intertwined with our curiosity. The apple reminds us that asking why is the first step toward discovery. Every scientific journey begins with noticing something ordinary and daring to wonder about it. Fact 4. Newton's universal law of gravitation. Newton didn't just notice gravity, he turned it into a formula. His universal law of gravitation states that every particle in the universe attracts every other particle, and the force depends on their masses and the distance between them. Simply put, bigger objects pull harder, and the farther apart they are, the weaker the pull. This law explained falling apples, orbital motions, and even the paths of comets. Suddenly, the heavens followed predictable rules, linking celestial and terrestrial phenomena under one law. By transforming a force into an equation, Newton gave humans the power to calculate, predict, and explore. With his law, we could send spacecraft to the moon, navigate satellites around Earth, and plot the motion of planets with precision. Newton's insight was revolutionary. It revealed that the universe is orderly and comprehensible, governed by forces we can understand and measure. Gravity became not just a pull on objects, but a bridge connecting the tiny with the cosmic. The universal law of gravitation demonstrates the beauty of mathematics in explaining nature. It shows that complex systems, planets, moons, comets, follow elegant rules. Newton didn't just explain falling apples, he unveiled a universal rhythm, a force linking every object across space and time. Fact 5. Why everything falls at the same rate. Have you ever dropped a rock and a feather? On Earth, air resistance slows the feather, but in a vacuum both hit the ground simultaneously. Gravity accelerates all objects equally, regardless of mass. It might feel counterintuitive. Heavier objects don't fall faster, but gravity doesn't care about weight. It's mass and distance that matter. This principle explains why astronauts float in orbit. They're in free fall around Earth, moving sideways fast enough to keep missing the planet. Gravity shapes motion consistently. From tiny particles to massive planets, all objects follow predictable paths under its influence. This universality is why physics works. We can calculate orbits, predict tides, and design spacecraft using the same principles that make apples fall. Understanding that gravity treats all objects equally allows humans to explore space, build technologies, and grasp the underlying order of the universe. It's a simple yet profound truth. The invisible hand of gravity touches everything, shaping motion in a predictable, elegant way. Fact 6. Gravity versus weight. What's the difference? Have you ever stepped on a scale and noticed your weight seems slightly different depending on where you are on Earth? That's because weight and gravity, though closely related, aren't the same thing. Gravity is the invisible force pulling objects toward each other, like Earth pulling you downward. Weight, on the other hand, is the measure of that pull on a specific object. Think of it like this. Gravity is the hand reaching out to pull you, and weight is how strongly that hand is tugging. Your mass, essentially the amount of stuff you're made of, never changes no matter where you go. But your weight does, because the strength of gravity can vary slightly depending on location. For example, on the Moon, gravity is roughly 1/6 of what it is on Earth. So someone weighing 150 pounds on Earth would feel like they weigh only 25 pounds on the Moon. This distinction explains why astronauts can jump higher or carry seemingly heavier loads in space. They're experiencing less weight, but their mass and thus inertia remains the same. Even subtle variations on Earth affect weight. You might weigh slightly less at the equator than at the poles due to the combination of Earth's rotation and the shape of the planet. Understanding the difference between mass, weight, and gravity gives us perspective on our daily lives and space exploration alike. It reminds us that weight isn't an inherent property, it's gravity in action, quietly shaping everything from how we stand to how spacecraft are launched. Fact 7. The role of mass in gravitational force. Mass is the heart of gravity. The more mass an object has, the stronger its gravitational pull. This is why Earth keeps the Moon in orbit, why the Sun commands the planets, and why black holes can bend light itself. Mass is like the currency of gravity. The more you have, the greater your influence. Even small objects have mass and attract other things, though the effect is so tiny we don't notice it. Think of two small magnets. They pull on each other, even if only slightly. Gravity works in a similar way, but its reach is infinite. It never turns off and acts across the entire universe. Mass also affects how objects move under gravity. Larger masses bend space more sharply, creating deeper wells in the fabric of the cosmos. This is why massive objects dominate their neighborhoods, holding moons, rings, and dust in orbit. Stars, planets, and even clusters of galaxies organize themselves according to the mass that shapes the gravitational landscape. Without mass, gravity wouldn't exist. It's the invisible voice of the universe, dictating motion, structure, and interaction. Every celestial dance, from the orbit of planets to the spiral of galaxies, is choreographed by mass acting through gravity. Fact 8. How distance weakens. Gravity is everywhere, but it isn't uniform. The farther two objects are from each other, the weaker the gravitational pull between them. Imagine stretching a rubber band. The closer and tighter it is, the stronger the pull. Pull it apart and the force drops dramatically. Gravity works the same way, diminishing with the square of the distance. This explains why we feel Earth's pull so strongly but barely notice distant planets or stars. Even though the Sun is enormous, its gravitational influence on a human is tiny because we are far away. Distance shapes the motion of planets, guides spacecraft, and even determines how galaxies form and interact. Gravity is patient. It reaches across vast distances, but the farther it reaches, the gentler it becomes. This property allows for complex cosmic structures. Planets orbit stars, moons orbit planets, and galaxies dance around each other, all because gravity acts over distance with predictable strength. Understanding how distance affects gravity helps us navigate both space and everyday life. It explains why satellites stay in orbit and why we can feel grounded on Earth, while the Sun and Moon exert subtler pulls. Gravity's reach is universal, yet it's delicately tuned by distance. Fact 9. Why gravity always pulls, not pushes. Here's something you can count on. Gravity only ever pulls. Unlike magnets, which can push or pull, or fans that blow objects away, gravity has no push mode. Every object with mass draws other objects toward itself, creating attraction everywhere in the universe. This might seem obvious when we drop something, but think bigger. Planets, stars, even light itself are all subtly pulled by gravity. It's one way nature shapes everything, from orbits to star formation to galaxy structure. Without this constant pull, nothing would cluster. The universe would be a thin, cold soup of particles drifting randomly, without planets, moons, or stars. Gravity's steady pull organizes chaos into order. It governs motion, holds systems together, and sets the stage for cosmic evolution. It's a silent rule that underlies every structure in the universe. Even more fascinating is how gravity's pull creates balance. Orbits, tides, and galactic rotations all depend on this invisible tug-of-war, where nothing can push, only attract. Gravity's one-way rule is simple, yet it powers the intricate dance of the cosmos. Fact 10. The universal gravitational constant. Newton's law of universal gravitation describes how objects attract each other, but to turn this idea into numbers, he introduced a crucial constant, g, the gravitational constant. It's the tiny number that tells us how strong gravity is between any two objects. Without g, we couldn't calculate or predict planetary motion, satellite trajectories, or the behavior of stars and galaxies. G is incredibly small, so small that you wouldn't feel its effect in everyday life between tiny objects like pens or books. Yet it's essential for everything from sending rockets into space to understanding black holes. It acts behind the scenes, ensuring that Newton's equations match the universe's behavior precisely. Every time scientists calculate the pull between two masses, G is quietly at work, keeping the cosmic math accurate. It bridges the gap between theory and reality, letting humans turn abstract forces into tangible predictions. The gravitational constant reminds us that even a seemingly simple law, gravity, requires careful measurement and precision. It's the secret ingredient that allows us to harness, explore, and understand the invisible pull that shapes everything. Fact 11. Einstein's theory of general relativity. Imagine living in a world where the rules of gravity suddenly change. That's essentially what Albert Einstein did for science in the early 20th century. Newton had given us a formula for gravity, a universal pull between masses, but Einstein asked a deeper, bolder question. What if gravity isn't just a force pulling objects, but a property of space itself? Einstein's theory of general relativity proposed that massive objects like planets, stars, and black holes warp the very fabric of space and time around them. Rather than thinking of gravity as an invisible hand tugging at objects, Einstein described it as a bending or curving of the cosmic stage on which everything moves. Suddenly, the universe became more like a trampoline. Drop a heavy ball in the center, and it dents the surface. That dent guides everything around it, dictating the paths of smaller objects nearby. This revolutionary idea explained phenomena that Newton couldn't fully account for, such as the subtle wobble in Mercury's orbit. General relativity revealed that gravity isn't just about attraction, it's about the geometry of the universe. Every planet, moon, and star moves along these curves, tracing paths dictated by the shape of space-time itself. Even modern technology relies on this insight. GPS satellites orbit Earth and must account for these effects, or our navigation would drift by miles. Einstein's vision transformed our understanding of gravity from a mysterious pull to an elegant dance of space and time. It's a perspective that continues to shape modern physics, from the orbits of planets to the behavior of light near massive objects. Gravity became not just a force, but a framework through which we understand the universe. Fact 12. How space and time are curved by mass. Picture the universe like a giant trampoline. Place a bowling ball in the center, and the sheet dips under its weight. That's how Einstein explained gravity. Massive objects bend space and time around them. The heavier an object, the deeper the dip, and the more influence it has over nearby objects. This curvature doesn't just affect motion, it affects time itself. Light bends around massive stars, creating breathtaking phenomena like gravitational lensing, where distant galaxies appear stretched or multiplied. Even planets feel these curves, subtly altering their orbits in ways Newton's equations couldn't predict. In Einstein's model, mass and space-time are partners in a cosmic dance. Mass tells space-time how to curve, and space-time tells mass how to move. It's a simple idea with profound implications. Every orbit, trajectory, and cosmic path is guided by the shape of space-time itself. Gravity is no longer just a pull. It's the architecture of reality, determining how objects move and even how time flows. Fact 13. The rubber sheet analogy explained. One of the clearest ways to visualize Einstein's concept is the rubber sheet analogy. Imagine a stretchy sheet held tight. Place a heavy ball in the center, it sinks, creating a dip. Now roll a smaller ball across the sheet, it spirals inward, drawn toward the heavier ball. That's how planets orbit stars and moons orbit planets. Of course, real space-time has 4 dimensions, so the analogy isn't perfect. But it conveys the core idea. Mass bends the space around it, and objects follow the curves. They aren't being pulled in the Newtonian sense. They're tracing the paths created by the warp of space itself. This simple image helps people understand why planets move the way they do, why light bends near massive stars, and why black holes trap everything that comes too close. Gravity isn't just a force, it's the shape of space, guiding every motion in the universe with invisible channels and wells. Fact 14. How Einstein replaced the concept of force. Before Einstein, gravity was a mysterious force acting at a distance. Newton imagined invisible lines pulling objects together, even across empty space. Einstein flipped this idea. There is no force tugging objects. Instead, they follow the natural paths defined by the curves of space-time. Think of a marble rolling on a warped surface. It moves along the dips naturally. Objects in space behave the same way. They follow the geometry around massive bodies. Gravity, then, is not a force reaching out. It's the shape of space directing motion. This shift changed physics forever. It influenced our understanding of black holes, cosmology, and even the expansion of the universe. Einstein's insight reminds us that sometimes the universe isn't about stronger forces, but about hidden structures and geometries guiding what we observe. Fact 15. Time, dilation, and gravity. Clocks run slower. Here's a mind-bending consequence of Einstein's theory. Gravity affects time. The stronger the gravitational field, the slower time passes. Near a massive object like a black hole, a clock ticks far more slowly than it would in empty space. This isn't science fiction. It's real and measurable. Satellites orbiting Earth must account for time dilation, or GPS signals would drift by miles in minutes. Even on Earth, the effect is tiny but present. Clocks at higher altitudes tick slightly faster than those at sea level because gravity is weaker. Time isn't absolute. It's flexible, shaped by gravity itself. In extreme environments like near black holes, the difference becomes dramatic. One day, understanding these effects might help humans navigate space where time flows differently, revealing how deeply gravity shapes not just motion, but the very fabric of reality itself. Fact 16. Gravitational waves, ripples in space-time. Imagine tossing a pebble into a calm pond and watching ripples spread outward. Now, scale that up to something unimaginably massive, like two black holes colliding billions of light years away. That cataclysmic event sends ripples across the very fabric of space and time. These are gravitational waves. Predicted by Einstein over a century ago, they were finally detected in 2015, confirming one of general relativity's most astonishing predictions. Gravitational waves carry information about their violent origins. When two black holes spiral toward each other and merge, they release immense energy, distorting space itself. These distortions stretch and squeeze everything they pass through, even light. Detecting them requires instruments of mind-boggling precision, able to measure shifts smaller than a proton's width. The Laser Interferometer, Gravitational Wave Observatory, or LIGO, achieved just that, opening a new window onto the cosmos. In a way, gravitational waves are the whispers of the universe. They travel across the void, carrying tales of collisions, mergers, and cosmic tremors that no telescope could ever reveal. Every ripple is a subtle reminder that gravity doesn't just shape objects, it communicates events across time and space. By listening to these waves, scientists can study phenomena that were once invisible, from the dance of black holes to the echoes of neutron star collisions. Gravitational waves transformed astronomy. Suddenly, the universe wasn't just something to look at, it was something to hear. The cosmos is alive with motion and energy, and gravity is its messenger, silently connecting distant events in ways both profound and beautiful. Fact 17. Proof of relativity. The 1919 eclipse experiment. Einstein's general relativity made bold predictions, and the world was skeptical. How could anyone prove that massive objects like the Sun could bend light? The answer came during a total solar eclipse in 1919. Astronomers travelled to remote parts of Africa and South America, setting up cameras to photograph stars near the Sun's obscured disk. Normally, the Sun's brilliance hides nearby stars, but during the eclipse its light was blocked, revealing the stars in the background. Comparing their positions to measurements taken when the Sun was elsewhere, scientists found a tiny but undeniable shift. The star's light had bent around the Sun just as Einstein predicted. His theory had passed its first dramatic test. The news spread quickly. Einstein, previously known mainly in academic circles, became a household name almost overnight. People marvelled that an abstract mathematical idea could have such a real, observable effect. The experiment demonstrated that gravity was more than a simple pull. It was a warp in space itself. This confirmation marked a turning point in physics. It showed that the universe isn't just a predictable machine of forces acting at a distance. As Newton had suggested, but a dynamic, curving fabric influenced by mass. It was a triumph of theoretical science, proving that imagination, mathematics, and careful observation could reveal the hidden structure of reality. Fact 18. Gravity's role in GPS accuracy. Here's a surprising truth. The GPS in your phone relies on Einstein. Satellites orbit hundreds of kilometers above Earth, moving fast and experiencing slightly weaker gravity than we do on the surface. According to relativity, this affects the passage of time. Time ticks differently for these satellites, faster than clocks on Earth. If engineers ignored this, GPS signals would drift by kilometers every day, making navigation almost useless. To fix this, satellites' clocks are carefully calibrated, accounting for both special relativity, due to speed, and general relativity, due to weaker gravity. When your phone tells you exactly where to turn, it's Einstein's theories quietly working behind the scenes. It's astonishing to think that the invisible bending of space and time around Earth, something we can't feel, is essential for everyday technology. Without understanding gravity at this level, modern navigation, aviation, and even disaster response would be far less precise. Fact 19. Einstein versus Newton. Two views of the universe. Newton gave us the laws of motion and gravity, portraying the universe as a clockwork machine where forces act invisibly across space. Einstein went further, revealing that gravity isn't a force at all, it's a curvature of space and time. Both perspectives are correct, depending on context. For everyday life, apples falling, planets orbiting the sun, Newton is simple and accurate. For extreme conditions, black holes, massive stars, or high speeds, Einstein reigns supreme. They're two lenses to understand the universe, each remarkable in its own right. Newton gives predictability. Einstein gives depth. Together, they allow us to navigate the cosmos, from a backyard experiment to the edges of space. Fact 20. How general relativity still rules modern physics. More than a century later, Einstein's ideas remain at the heart of modern physics. From predicting black hole collisions to guiding spacecraft across the solar system, general relativity explains phenomena that Newton's laws can't touch. Even in everyday tech like GPS, his equations operate quietly behind the scenes. Physicists continue to test and challenge the theory, seeking ways to merge it with quantum mechanics. Yet after decades of scrutiny, general relativity consistently holds. It's a reminder that understanding gravity isn't just academic. It's essential for navigating the universe and grasping its hidden order. Einstein transformed gravity from a simple pull into a guiding architecture of space and time, showing that the universe is far stranger and far more beautiful than we ever imagined. Fact 21. Why we stay grounded, Earth's pull. Ever wondered why, no matter how high you jump, you always come back down? That's Earth's gravity at work. The planet is massive, and its mass generates a pull that keeps everything, from oceans to people, firmly on the ground. We tend to take this for granted, but without gravity, life as we know it would be impossible. Gravity acts like an invisible leash connecting us to the planet. Even when you run, jump, or climb, gravity is quietly asserting control, keeping your feet tethered to Earth's surface. Mountains stay rooted, rivers flow downhill, and the atmosphere clings around the globe, all thanks to this constant pull. Every object, every molecule, experiences this same force. We don't notice it because it's consistent and steady, yet its effects dominate our daily lives in ways we rarely think about. It's not just about falling, it's about the invisible architecture that holds the planet together. Without gravity, the Earth would be a chaotic cloud of particles, oceans would drift away, and we wouldn't even be able to walk without floating off into space. Gravity also gives us a sense of stability, our balance, movement. And even the way we interact with the world depend on it. From the tiniest ant to the tallest mountain, every object participates in this pull. It's an unseen anchor, silently organizing the planet and shaping the environment we live in every single day. Fact 22. Gravity's strength at the equator versus the poles. Gravity isn't exactly the same everywhere on Earth. It's slightly weaker at the equator and a bit stronger at the poles. This difference comes from two main factors: Earth's rotation and its shape. The planet isn't a perfect sphere, it's slightly flattened at the poles and bulging at the equator. As Earth spins, centrifugal force pushes objects outward slightly more at the equator. Combine that with the planet's shape and you get subtle variations in gravitational pull. A scale at the equator might register slightly less weight than the same scale at the poles. These differences are small but measurable, and they have practical applications like calibrating satellites, designing scientific instruments, and even understanding tectonic movements. Gravity is dynamic. influenced not just by mass but also by rotation, shape, and local mass distribution. Subtle variations reveal clues about the Earth's interior, including the density of rocks, the movement of magma, and the behavior of tectonic plates. Even tiny differences in gravitational strength tell a story about the planet's structure and help scientists understand how Earth functions as a system. Fact 23. How gravity shapes Earth's oceans. Gravity doesn't just hold us down, it shapes the oceans too. The water covering Earth isn't spread evenly. It's molded by the planet's gravitational pull. Mountains, valleys, and underwater ridges create variations called geoid anomalies, where local sea levels rise or fall slightly. Gravity also interacts with Earth's rotation, producing bulges in the oceans. These bulges drive currents and influence ocean circulation, which in turn affects climate and weather patterns. Without gravity, oceans wouldn't stay in their basins, tides wouldn't exist, and life in the seas would be drastically different. Every wave and current is subtly guided by gravity's invisible hand. From calm lakes to vast oceans, this constant pull keeps water moving in predictable patterns. It ensures that marine ecosystems thrive, coastlines remain stable, and the hydrological cycle continues uninterrupted. Gravity is the quiet sculptor of our planet's watery world. Fact 24. Tides. The moon's gravitational dance. Tides are one of the most visible ways we experience gravity. They rise and fall because of the moon's pull, which creates bulges in Earth's oceans. When the moon is overhead, water is drawn toward it, producing high tide. On the opposite side, inertia creates another bulge. The sun also affects tides, though its influence is weaker. During new and full moons, the sun and moon align, producing especially high spring tides. During quarter moons, their pulls partially cancel, leading to lower neap tides. Tides are more than a coastal spectacle. They shape marine ecosystems, affect shipping routes, and even drive ocean currents that influence global climate. The moon's quiet gravitational dance is a reminder that celestial bodies are deeply interconnected with life on Earth. Every rise and fall of the tide is a rhythmic heartbeat of the planet, orchestrated by the invisible hand of gravity. Fact 25. Gravity and the Earth's core. Gravity doesn't stop at the surface. It reaches deep into Earth's core. The planet's mass creates immense pressure, compressing the inner layers and keeping the dense core tightly packed. This gravitational compression generates heat, driving convection in the molten outer core and producing Earth's magnetic field. Without gravity shaping the core, the planet wouldn't have a magnetic shield to protect life from harmful solar radiation. Gravity also keeps the inner core solid despite extreme temperatures, holding the entire structure of Earth together. Every layer, from the crust to the core, is molded and maintained by this silent, unyielding force. Gravity isn't just a pull we feel, it's the invisible architect of our planet, orchestrating everything from oceans to molten rock deep beneath our feet. It's the force that makes Earth habitable and keeps the machinery of our planet running smoothly, every second of every day. Fact 26. How gravity creates air pressure. We often take the air around us for granted, but gravity is the reason it stays pressed firmly against Earth. Air isn't just empty space, it's made of countless tiny molecules, each moving and bouncing randomly. Gravity pulls these molecules downward, creating pressure that we feel all the time. This pressure is strongest near Earth's surface, where the air is densest and gradually decreases as you climb higher into the atmosphere. Think about hiking up a mountain. As you ascend, the air feels thinner. Your lungs have to work harder to get enough oxygen, because there's less air being pulled toward you by gravity. This isn't just a quirk of high-altitude living, it's a direct consequence of gravity organizing the atmosphere. Without gravity, the air wouldn't hug the planet. It would drift into space, leaving Earth a barren, airless rock. Air pressure isn't just about breathing. It shapes the weather, drives winds, and even affects how airplanes fly. Planes rely on differences in air pressure over their wings to generate lift. Without gravity holding the atmosphere in place, aviation as we know it would be impossible. Storms, clouds, and rain are all guided by pressure gradients created by gravity's invisible hand. Gravity organizes the atmosphere like a quiet conductor, keeping oxygen close enough for life to thrive, maintaining temperatures, and ensuring that weather patterns follow predictable rhythms. Every gust of wind, every gentle breeze, is part of a dance orchestrated by gravity. Even something as simple as taking a deep breath is made possible because the air molecules are pulled downward consistently. In essence, gravity doesn't just pull objects to the ground, it presses the very air we need to survive against the planet, creating a livable environment. From the deepest valleys to the highest peaks, this unseen force shapes every breath we take and every gust of wind that brushes past our skin. Air pressure is gravity in action, silently sustaining life every moment of every day. Fact 27. Why you weigh less on a mountain. Ever stepped on a scale at high altitude and noticed it reads slightly lower? It's not a glitch, it's gravity at work. Gravity isn't perfectly uniform across Earth. The higher you climb, the farther you are from Earth's centre of mass, and the weaker the gravitational pull becomes. On a tall mountain, you weigh just a tiny bit less than at sea level, not enough to notice casually, but measurable with precise instruments. This small effect highlights an important principle. Gravity depends on distance. The farther an object is from the source of mass, the less it is pulled. Astronauts floating in orbit experience this in a more extreme form. They're still under Earth's gravitational pull, but their sideways motion allows them to constantly fall around the planet, creating the sensation of weightlessness. On a mountain, you're far from this extreme, but it's the same principle at work. Even subtle variations in gravity affect the world around us. Geophysicists study these differences to map Earth's interior, identifying dense rock formations, underground water, and even mineral deposits. The slight decrease in weight on a mountain is a tiny glimpse into the complex ways Earth's mass and shape influence gravitational pull. Gravity's consistency is deceptive. We take it for granted, yet small shifts like this remind us that it's a dynamic force, subtly influenced by distance, shape, and mass distribution. Your body might feel the same at the top of a peak, but the universe's invisible tug has changed ever so slightly. That difference, though small, is a testament to gravity's intricate reach across the planet. Fact 28. Measuring Earth's gravity, the GRACE satellites. Scientists have an extraordinary way to measure gravity across Earth using the GRACE, Gravity Recovery and Climate Experiment satellites. These twin spacecraft orbit Earth in tandem, tracking tiny variations in the planet's gravitational pull. Differences arise because of mass distribution. Mountains, oceans, ice sheets, and even groundwater affect the pull slightly. By measuring minute changes in the distance between the satellites, scientists can map Earth's gravity with incredible precision. These measurements reveal shifting ice sheets in Greenland and Antarctica, groundwater depletion, and even changes in ocean mass due to currents and tides. Gravity becomes a tool, not just a force, allowing us to understand the planet's evolving systems. GRACE data has transformed climate science. It helps scientists track melting glaciers, monitor droughts, and predict sea level rise. Gravity in this sense isn't just a pull. It's a window into how Earth changes over time. The satellites demonstrate that gravity isn't static. It's a living map of mass moving across the planet. Every tiny gravitational shift tells a story. Seasonal rainfall, tectonic activity, and ice melting all leave their mark. With GRACE, we can see these changes through the lens of gravity, revealing patterns invisible to the naked eye. It's a reminder that gravity doesn't just hold us down. It carries information about the planet itself, quietly shaping life while telling its story. Fact 29. How gravity influences rivers and erosion. Gravity is the hidden hand behind rivers, erosion, and the shaping of landscapes. Water flows downhill, pulled relentlessly toward lower elevations. As it moves, it carries sediment, carving valleys, canyons, and deltas over millennia. Mountains are gradually worn down, and plains are built up, all under the patient, steady pull of gravity. This force also drives landslides, soil transport, and even the formation of caves. Without gravity, rivers would stagnate, sediments wouldn't move, and landscapes would remain frozen in place. Gravity is the slow sculptor, shaping the planet one drop of water at a time. Erosion isn't violent, it's persistent. Rain, snowmelt, and rivers are constantly guided by gravity. Over thousands and millions of years, the small pull of gravity produces massive transformations, Every meandering river, every canyon, and every cliff tells a story of water obeying gravity's quiet command. Even human engineering relies on this understanding. Dams, canals, and flood controls all depend on predicting how gravity moves water. In a very real sense, gravity choreographs the flow of life-giving water across the planet, linking hydrology to geography in an unbroken chain. Fact 30. The subtle shift in gravity. Over time, gravity on Earth isn't perfectly constant. It subtly shifts over time due to factors like melting ice sheets, tectonic movements, and seasonal water distribution. Even heavy rainfall can create small, measurable changes in local gravity. Instruments like GRACE satellites can detect these tiny variations, allowing scientists to monitor groundwater depletion, glacial melt, and shifts in ocean currents. Gravity becomes a tool to track Earth's evolution, revealing patterns that affect climate, ecosystems, and human activity. These subtle shifts remind us that gravity isn't static, it's dynamic. The planet is alive, moving and changing, and gravity reflects that motion. From the redistribution of ocean mass to the shifting of tectonic plates, even the smallest mass changes produce detectable effects. Gravity is more than a pull, it's a storyteller. It quietly records the planet's transformations, linking the movements of water, rock, and ice across centuries. Every change, however small, is part of an ongoing conversation between Earth and the force that holds it together. Fact 31. The Moon's gravity, 1/6 of ours. Imagine taking a leap on the Moon. You'd soar 6 times higher than on Earth, moving gracefully in slow-motion arcs before landing with a soft thump. That's because the Moon's gravity is only about 1/6 as strong as Earth's. It's still pulling you downward, but far more gently. This weaker gravity transforms how everything behaves on the lunar surface. Astronauts can carry heavy tools and rock samples with ease, bouncing across craters like giants. Dust and small debris move slowly, settling over long periods rather than quickly eroding the landscape. That's why the Moon's surface looks so rugged and cratered even after millions of years. The lack of strong gravity means erosion is minimal. Gravity also allows the Moon to influence Earth. Its pull is enough to create tides, subtly tugging on oceans in rhythmic patterns. Over long periods, these gravitational interactions even affect Earth's rotation, gradually lengthening our days. Despite being smaller and lighter, the Moon demonstrates that gravity isn't just about weight. It's a force of connection and influence. Even tiny variations in lunar gravity have practical consequences. When planning moonwalks or building lunar bases, scientists have to account for reduced weight and the different dynamics of motion. Walking, jumping, and landing all require recalibration, showing that gravity shapes every action, even in familiar ways. The Moon reminds us that gravity is relative. It isn't a fixed pull. It depends on mass, distance, and context. Stepping on another world, we see gravity's fingerprints everywhere, organizing the cosmos in ways both subtle and profound. From tides to astronaut jumps, the Moon's gentle pull is a constant lesson in how the universe stays connected. Fact 32. The Sun's gravitational grip on the solar system. The Sun is the anchor of our solar system. Its immense gravity holds planets, comets, and asteroids in orbit, guiding them along paths that have remained stable for billions of years. Without the Sun's pull, Earth and its neighbouring planets would drift off into space, lost in the vast void. Every object feels the Sun's influence. Mercury zips close to it, Neptune orbits far away, and even distant comets trace elongated paths under its gravitational hand. The Sun's massive presence warps space-time, creating a deep well that everything nearby must navigate. Planets move along these curved paths, held in delicate balance between motion and pull. The Sun's gravity isn't just a binder, it's a guide. Spacecraft can exploit its pull using gravitational slingshots, gaining speed or changing trajectory without using fuel. This dynamic role of gravity shows that it's both a stable anchor and a tool for motion, shaping orbits, trajectories, and even the destiny of celestial bodies. Without this force, the solar system would be chaos. Planets would collide, comets would escape, and the familiar order of our skies would vanish. Gravity is the invisible script behind the cosmic dance, and the Sun writes the most influential lines, orchestrating a balance that has endured for eons. Fact 33. How planets stay in orbit. Why don't planets fall into the sun or drift off into space? Gravity holds the answer. A planet's motion is a delicate balance. Its forward momentum wants to carry it straight, while the sun's gravity pulls it inward. The result is an orbit, a constant freefall around the star, never colliding, never escaping. The same principle applies to moons, like our own. Earth's moon is perpetually falling toward us, yet it moves fast enough sideways to miss, tracing a nearly perfect circle or ellipse. Orbits are elegant solutions to gravity's pull, showing how motion and force combine to create cosmic harmony. Even comets, asteroids, and spacecraft obey these rules. Launching satellites or navigating spacecraft requires precise calculations, balancing velocity and gravitational pull. The universe operates like an intricate clockwork, each orbit a testament to gravity's quiet but unyielding control. Gravity is both restrictive and liberating. It keeps planets in line, yet allows them freedom to move in paths dictated by the interplay of mass and motion. Without it, the universe would be a scattered mess. With it, orbits become a cosmic choreography. Fact 34. The gravitational tug-of-war between Earth and the moon tides are the most visible example of a gravitational tug-of-war between Earth and the moon. The moon's pull draws water toward it, creating high tides. At the same time, Earth's rotation and inertia form another bulge on the opposite side. The sun also joins the dance, sometimes amplifying or reducing the effect. This tug-of-war isn't just a coastal spectacle, it affects life on Earth. Ocean currents driven by tides regulate climate, shape ecosystems, and even influence marine migration patterns. Over billions of years, these gravitational interactions have subtly altered Earth's rotation and the moon's orbit, gradually lengthening our days. Gravity acts as a cosmic conversation between Earth and its nearest celestial neighbour. Every tide, from gentle lapping waves to massive storm surges, is evidence of this invisible dialogue. Life on our planet, both human and marine, is in part orchestrated by this constant interplay of pulls and counterpulls. Even on a smaller scale, the moon's influence guides rivers, sediment, and coastlines, shaping the very land we inhabit. It's a reminder that gravity isn't isolated. It's relational, connecting planets and moons, oceans and land, in a continuous gravitational symphony. Fact 35. Gravity and planetary rings. Saturn's rings are one of the most beautiful examples of gravity's artistry. These rings are composed of countless particles, from tiny dust grains to massive boulders, all held in delicate orbit by the planet's pull. Too close, and particles might crash into Saturn or clump into moons. Too far, and they would drift into space. Moons and minor satellites nearby influence the rings, creating gaps, waves, and spirals within them. Each feature is a direct consequence of gravitational interaction, showing that even subtle forces can produce breathtaking structures. Gravity acts as both sculptor and choreographer. It organizes chaos into elegant patterns, controlling motion with precision. Rings are not static. They evolve as particles collide, orbit, and respond to nearby gravitational fields. The result is a dynamic, ever-changing display that captivates astronomers and casual observers alike. Planetary rings remind us that gravity shapes more than planets and stars. It creates the intricate beauty of the universe, turning randomness into patterns and chaos into harmony. From the smallest particles to the largest moons, everything is participating in gravity's grand ballet. Fact 36. Escape velocity. Breaking free of gravity. Have you ever wondered what it takes for a rocket to leave Earth and head into space? It's all about escape velocity, the minimum speed an object must reach to overcome a planet's gravity without falling back down. For Earth, that speed is around 25,000 miles per hour. That's incredibly fast, but it's the threshold that allows spacecraft to break free and journey into orbit or beyond. Escape velocity depends on both the mass of the planet and the distance from its center. Larger planets, like Jupiter, have much higher escape velocities, while smaller ones, like the Moon, are easier to leave. It's not just about fuel or engines, it's about overcoming gravity's relentless pull. Even if a rocket has enough power to lift off, it must reach the speed where gravity can no longer pull it back. In a way, escape velocity illustrates the invisible chains that gravity creates. Every object on Earth is bound to the planet, and only a precise combination of speed and trajectory can break those bonds. It's a beautiful example of physics in action, showing how motion, mass, and distance interact to define what's possible in space exploration. Fact 37. How gravity shapes the motion of comets. Comets are some of the most dramatic travellers in the solar system, with long tails blazing through space. Their paths, however, are not random. They are dictated by gravity. The sun's immense pull bends the trajectory of comets, guiding them along elliptical or parabolic orbits. Gravity from planets also plays a role, nudging comets into new paths or even capturing them temporarily. Some comets swing close to Earth periodically because of this gravitational guidance, creating predictable meteor showers. Even the tiniest tweak from Jupiter's massive pull can dramatically alter a comet's journey over time. Without gravity, comets would drift aimlessly into space. With it, their movements become part of a cosmic choreography, showing how even distant objects are connected through invisible forces. Every tail streaking across the night sky is, in essence, following the instructions written by gravity. Fact 38. Gravitational slingshots in space missions. Space agencies have a clever way to harness gravity to speed up spacecraft: gravitational slingshots. By carefully flying a spacecraft close to a planet, engineers can use the planet's gravity to change its speed and direction, like a cosmic swing. This technique saves fuel and makes missions to distant planets feasible. For instance, the Voyager probes used multiple slingshots around Jupiter and Saturn to reach the outer solar system. The spacecraft gains speed while the planet loses an almost imperceptible amount of its orbital momentum. It's a brilliant example of using gravity not as an obstacle, but as a tool. Gravitational slingshots demonstrate that gravity isn't just a force to resist, it's a force to work with. By understanding it, humans can travel farther, faster, and more efficiently, turning an invisible pull into a powerful launchpad for exploration. Fact 39. The Lagrange points, islands of stability in space. Somewhere between two massive objects like Earth and the Moon, there are points where gravity and orbital motion balance perfectly. These are called Lagrange points, and they're essentially cosmic sweet spots, where spacecraft can remain stable with minimal fuel. There are 5 such points in any two-body system, each with unique properties. Lagrange points are ideal for space observatories, satellites, and even potential space stations, because they allow long-term positioning without constant adjustments. NASA's James Webb Space Telescope, for example, operates near one of these points. Lagrange points reveal the subtle, precise nature of gravity. It's not always a simple pull toward a planet or star. In some places, opposing forces can create stability, offering human ingenuity a perfect perch in space. Fact 40. Gravity and the shape of planets. Gravity shapes planets into near spheres. It pulls matter toward the center, smoothing out irregularities and giving planets their rounded appearance. Smaller planets and moons may have more irregular shapes, but large bodies like Earth, Jupiter, or Saturn are shaped almost perfectly by gravity's relentless pull. Gravity also affects rotation. As a planet spins, it bulges slightly at the equator due to centrifugal forces, creating an oblate shape rather than a perfect sphere. Even mountains, valleys, and oceans conform to the planet's gravitational balance. In essence, gravity is the invisible sculptor of planets, controlling both their overall shape and the finer details of their surfaces. Every curve, every bulge, and every dip tells a story about the delicate balance between pull and motion in the cosmos. Fact 41. How a star collapses into a black hole. A black hole begins life as a massive star. For millions of years, the star burns brightly, balancing gravity with the pressure from nuclear fusion at its core, but eventually the fuel runs out and the star can no longer resist its own weight. Gravity takes over, crushing the core inward. The collapse happens incredibly fast. The core compresses into an extremely dense point called a singularity, where matter is packed tighter than atoms. The outer layers may explode outward as a supernova, lighting up space for a brief, brilliant moment. What remains is a black hole, a region where gravity is so strong that nothing, not even light, can escape. It's a dramatic transformation, from a shining beacon to an invisible yet immensely powerful object. Black holes are extreme examples of what gravity can do when there's no force left to push back. They teach us that gravity isn't just gentle pull, it can dominate, reshape, and redefine entire stars. Fact 42. What is the event horizon? The event horizon is the point of no return surrounding a black hole. Cross it and escape becomes impossible, even for light. It's like a cosmic boundary. Outside, physics behaves normally. Inside, gravity rules without mercy. Think of it like a waterfall in space. You can float near the edge safely, but once you drift past, the pull becomes absolute. The event horizon doesn't mark the black hole itself. That's the singularity at the center. It marks the invisible surface beyond which nothing returns. Astronomers can detect black holes indirectly by observing the event horizon's effects on nearby matter. Gas and dust swirl violently around it, heating up and emitting X-rays before disappearing. The event horizon is both a boundary and a clue, helping scientists study objects that would otherwise be completely invisible. Fact 43. Spaghettification, the stretching power of gravity. Near a black hole, gravity isn't just strong, it's extreme. If you fell toward 1 foot first, the pull on your feet would be far stronger than on your head. This difference stretches you into a long, thin shape in a process scientists call spaghettification. It sounds cartoonish, but it's real physics. The closer you get to the singularity, the more intense the stretching becomes. The gravitational gradient is so powerful that it tears apart anything that ventures too close. It's a dramatic demonstration of gravity's ability to dominate every physical law in extreme environments. Spaghettification shows us that gravity isn't just a gentle tug. It can become an unstoppable, universe-shaping force under the right conditions. Fact 44. Time stops at the edge of a black hole. Einstein's theory of general relativity changed the way we think about gravity, not just as a force, but as a warping of space and time. One of the most astonishing consequences of this is how gravity affects time itself, a phenomenon called gravitational time dilation. Near a black hole, this effect becomes extreme, reaching levels that challenge our everyday understanding of reality. Imagine you are hovering near the edge of a black hole's event horizon, the invisible boundary beyond which nothing can escape. From your perspective, time would feel normal. You could think, breathe, and look around as usual. But for someone far away, watching from a safe distance, everything you do would appear to slow down dramatically. In fact, to that distant observer, it would seem as if you are frozen in place, suspended at the very edge, never actually crossing the threshold. What seems instantaneous to you stretches into eternity for them. This is not science fiction. It's a direct prediction of Einstein's equations. Gravity doesn't just pull on matter, it also pulls on time itself. The stronger the gravitational field, the more it slows the passage of time. Around a black hole, where gravity is unimaginably intense, this slowing becomes extreme. The closer you get to the event horizon, the slower your clock ticks relative to someone far away. If you could somehow survive and look back at the distant universe, you would see galaxies and stars racing forward at incredible speeds, while your own time continues normally, almost frozen compared to the cosmos outside. Gravitational time dilation near a black hole has fascinating implications. It means that black holes are not only regions of immense density and crushing gravity, but also zones where the very flow of time is stretched and distorted. Astronauts and explorers venturing close to these cosmic giants would experience a universe radically different from ours, where seconds and hours are no longer universal. The effect is so pronounced that near a supermassive black hole, a few minutes spent near the event horizon could correspond to years passing in the rest of the universe. This extreme behavior also influences how we detect and study black holes. Light and matter spiraling around the event horizon appear stretched and slowed to distant observers, creating unique observational signatures. Gravitational time dilation is a key part of understanding phenomena like accretion disks, relativistic jets, and the glowing rings captured by the Event Horizon Telescope. Ultimately, time dilation at the edge of a black hole is a mind-bending reminder that gravity is far more than a simple pull. It shapes the very fabric of the universe. It alters not just where things move, but when they move. Space and time are intertwined, and gravity is the invisible hand bending both, showing us a universe far stranger, more beautiful, and more complex than our daily experiences suggest. Near a black hole, time itself becomes a malleable, cosmic force, a humbling testament to the power and mystery of gravity. Fact 45. The first image of a black hole. In 2019, humanity got its first real glimpse of a black hole. Using the Event Horizon Telescope, astronomers captured an image of a glowing ring surrounding the dark shadow of the supermassive black hole in galaxy M87. It was historic. For the first time, we could see the edge of an object previously considered invisible. The image confirmed theories about how matter behaves near the event horizon and provided visual proof of something we had only calculated and imagined for decades. Gravity had created something we could observe directly, showing both its power and the ingenuity of human exploration. Fact: 46 supermassive black holes at galactic centers. Most galaxies, including our own Milky Way, hide a secret at their centers: a supermassive black hole. These aren't ordinary black holes. They weigh millions or even billions of times the mass of the Sun. Despite their size, they occupy a tiny region of space relative to the galaxy. Yet their gravitational influence shapes the motion of stars, gas, and dust around them. Imagine a bustling city where all the traffic, buildings, and people orbit a hidden, invisible force at its center. That's what stars do around a supermassive black hole. While the black hole itself is invisible, its presence is undeniable. Stars zip around it at incredible speeds, gas swirls in luminous accretion disks, and jets of energy shoot outward at nearly the speed of light. These black holes grow over time by consuming gas, dust, and even stars, slowly shaping their host galaxies. Scientists believe that the size of a galaxy's central black hole is linked to the galaxy's evolution, suggesting a deep connection between these cosmic giants and the structures they inhabit. Observing supermassive black holes is a challenge. They're surrounded by blinding radiation from infalling matter, making direct observation almost impossible. Yet we can detect their influence through stellar motions, X-ray emissions, and recently images of their shadow, like the one captured in galaxy M87. These cosmic titans remind us that gravity isn't just a local force, it can dominate entire galaxies, quietly orchestrating the dance of billions of stars. Supermassive black holes are both the hidden anchor and the ultimate gravitational rulers of their galaxies, showing the universe's extremes in one concentrated spot. Fact 47. How black holes. Warp-like gravity doesn't just pull matter, it bends light itself. Black holes with their immense mass create such strong curvature of space-time that light passing nearby is distorted, producing some of the most spectacular phenomena in the cosmos. This effect, called gravitational lensing, can magnify distant galaxies or create multiple images of the same object. Near a black hole, light follows curved paths around the intense gravity, forming bright rings, arcs, and shadows. It's as if the black hole acts like a cosmic magnifying glass, bending light in ways that reveal the universe behind it. Close to a black hole, light can orbit multiple times before escaping, or fail to escape entirely if it crosses the event horizon. These distortions allow astronomers to infer the black hole's mass, spin, and even the properties of surrounding matter. Without this light-bending effect, our understanding of black holes and distant galaxies would be far more limited. Gravity's ability to warp light shows its influence reaches beyond what we can see. It reminds us that space is not just a backdrop, it's an active participant in shaping the universe, guiding everything, including light, along the curves carved by massive objects. Fact 48. Hawking radiation and black hole. Evaporation, black holes were long thought to be eternal, consuming matter endlessly with no escape. But in 1974, Stephen Hawking revolutionized our understanding. He proposed that black holes aren't entirely black. They emit tiny amounts of radiation, now known as Hawking radiation. This radiation arises from quantum effects near the event horizon. Particle-antiparticle pairs constantly pop into existence from the vacuum of space. Occasionally, one particle falls into the black hole, while the other escapes, stealing a tiny bit of the black hole's mass. Over unimaginably long periods, this process can cause black holes to slowly evaporate. Hawking radiation is extremely weak for large black holes, making it nearly impossible to detect directly. Yet the theory has profound implications. It links gravity, quantum mechanics, and thermodynamics, suggesting that even the most extreme gravitational objects obey the subtle rules of quantum physics. This idea transforms black holes from eternal devourers to dynamic objects, slowly shrinking and losing energy. It's a reminder that gravity may be immense, but it doesn't operate in isolation. Other forces of nature play a quiet, persistent role, even at the edges of space-time. Fact 49. Black hole. Mergers and gravitational waves. When two black holes collide, the universe trembles. Their merger sends ripples through space-time called gravitational waves. Predicted by Einstein a century ago, these waves were finally detected in 2015 by LIGO, confirming a long-standing prediction of general relativity. Black hole mergers are violent events. As the black holes spiral inward, they radiate enormous energy in the form of gravitational waves, slightly altering space itself as they pass. These ripples move at the speed of light, stretching and compressing space along their path. Detection of gravitational waves has opened a new way of observing the universe. Unlike light, which can be blocked or absorbed, gravitational waves travel freely, carrying information about events billions of light-years away. Each detected wave tells a story about the masses, spins, and distances of merging black holes. Mergers highlight gravity's power on a cosmic scale. It not only controls motion but can release energy rivaling all the stars in the observable universe combined, even if only for a fraction of a second. These collisions reveal the universe's most extreme dynamics, showcasing gravity's ability to reshape space and time itself. Fact 50. Could tiny black holes exist? Black holes aren't all massive and cosmic. Some theories suggest tiny primordial black holes might exist, formed in the early universe from extreme density fluctuations. Unlike stellar or supermassive black holes, these could be as small as an atom but incredibly dense. Tiny black holes would have fascinating properties. They could evaporate quickly due to Hawking radiation, emitting bursts of energy before disappearing. If they existed today, they might explain some mysterious cosmic phenomena, like certain forms of dark matter or unexplained gamma-ray signals. Detecting them is incredibly challenging. Their small size and brief lifetimes make them nearly invisible. Yet, the possibility of tiny black holes reminds us that gravity operates at every scale, from the vast cosmic giants to potential microscopic objects, shaping the universe in ways we are only beginning to explore. Fact 51. How gravity formed the first stars. In the beginning, the universe was a dark, nearly featureless expanse filled with hydrogen and helium. Gravity was the hidden architect that transformed this simple gas into the first stars. Tiny fluctuations in density allowed gravity to pull matter together, slowly building clumps that grew denser and hotter over millions of years. As the gas compressed, pressure and temperature rose at the core of each clump until nuclear fusion ignited. A new star was born, shining for the first time in a universe that had been entirely dark. These early stars, called population 3 stars, were massive, hundreds of times the mass of our Sun, and they produced the first heavy elements through fusion. Gravity didn't just create stars, it dictated their size, lifespan, and distribution. Without this invisible force, the universe would have remained a cold, empty expanse. It was gravity that sculpted light from darkness, laying the foundation for galaxies, planets, and eventually life itself. Fact 52. The birth of galaxies. Through gravitational clumping. Once stars formed, gravity continued its work, pulling stars and gas into larger structures, galaxies. Regions with slightly higher mass attracted more matter, forming clusters that became the seeds of galaxies. Over billions of years, gravity's relentless pull created spirals, ellipses, and irregular galaxies, each shaped by the motions and interactions of their stars. Galaxies are not static. They rotate, collide, and merge, all under gravity's guidance. Dark matter, an invisible component, adds extra gravitational pull, helping galaxies hold together despite their rapid rotation. Gravity is the cosmic glue, making sure stars don't drift apart and providing the architecture for the vast structures we observe today. Understanding galaxy formation is like watching a slow-motion dance choreographed by gravity. Every swirl, cluster, and spiral arm tells the story of matter pulled together over billions of years, forming the universe we see today. Fact 53. Dark matter. The invisible mass. Holding galaxies together. When astronomers measured how fast stars orbit their galaxies, they noticed something strange. Stars on the edges moved far faster than gravity from visible matter alone could explain. Something invisible was providing extra pull. This mysterious substance is called dark matter. Dark matter doesn't emit light, reflect it, or interact with normal matter except through gravity. Yet its presence is essential. Without it, galaxies would fly apart, unable to hold themselves together. It's like a hidden skeleton, providing structure to the visible universe. Gravity reveals dark matter's influence, shaping galaxy rotation, cluster formation, and even the cosmic web, the vast filaments of matter stretching across the universe. Though we can't see it, gravity makes dark matter's presence undeniable. Fact 54. Dark energy, gravity's opposite force. If gravity pulls matter together, dark energy pushes the universe apart. Observations of distant galaxies show that the universe isn't just expanding, it's accelerating. This mysterious energy counteracts gravity on cosmic scales, driving galaxies farther apart at ever-increasing speeds. Dark energy is invisible, uniform and pervasive. While gravity binds stars into galaxies, dark energy acts across vast distances, shaping the universe's fate. Without it, cosmic expansion would slow, and the universe might collapse. With it, we live in an ever-expanding cosmos, where gravity and dark energy are in constant balance. This cosmic tug-of-war defines the large-scale structure of the universe and shapes its ultimate destiny, reminding us that gravity, powerful as it is, isn't the only force at play in the cosmos. Fact 55. How gravity shapes. Galaxy collisions. Galaxies are not isolated islands. They drift through space, sometimes colliding in spectacular cosmic encounters. Gravity is the director of these interactions, pulling stars, gas, and dark matter into complex orbits during collisions. When galaxies collide, their shapes stretch and distort. Tidal tails form, and new stars ignite from compressed gas clouds. Black holes at galactic centers may merge, releasing gravitational waves. Despite the chaos, individual stars rarely collide because they're so far apart. It's gravity that choreographs the grand-scale motion, creating stunning visual phenomena. Galaxy collisions show gravity as both a destructive and creative force, reshaping the universe while building new structures and sparking star formation. Over billions of years, these encounters have played a crucial role in forming the galaxies we see today. Fact 56. The role of gravity in star clusters. Star clusters are neighborhoods in space, where stars gather in groups bound together by gravity. Some clusters are loose, like open clusters, while others are dense and spherical, called globular clusters. Gravity acts like an invisible thread, holding these stars together despite their rapid motion. Within a cluster, stars interact gravitationally, tugging on each other and sometimes exchanging energy. Over millions of years, these interactions can change a star's orbit, or even eject it from the cluster entirely. Gravity ensures that clusters are not random gatherings of stars, but dynamic, evolving systems. Clusters also give astronomers clues about stellar evolution. Because the stars in a cluster form around the same time, their differences in brightness and color reveal how mass and gravity influence their life cycles. In this way, gravity is both the glue that holds stars together and the force that shapes their destinies. Fact 57. How supernovae battle gravity stars spend their lives fighting gravity. For millions or billions of years, nuclear fusion produces outward pressure that balances the inward pull of gravity. But in massive stars, when fuel runs out, gravity wins. The core collapses in an instant, and the outer layers rebound in a titanic explosion called a supernova. This violent release of energy can outshine entire galaxies for a brief period. Gravity, despite being the trigger, continues to shape the aftermath. The collapsed core may form a neutron star or black hole, while surrounding gas is flung outward, seeding the cosmos with heavy elements like gold and iron. Supernovae show gravity's dual role. It destroys by collapsing matter, but also enables creation, distributing the elements that form planets, life, and future stars. It's a dramatic example of gravity as both a destroyer and a creator in the universe. Fact 58. Gravity and the expansion of the universe. The universe is expanding, with galaxies moving away from each other. Gravity, however, is trying to slow this expansion. On smaller scales, like within galaxies or clusters, gravity dominates, keeping stars bound. On cosmic scales, the expansion overwhelms gravity, letting galaxies drift apart. This tension between gravity and expansion defines the universe's large-scale structure. In the early universe, gravity pulled matter into dense regions, forming stars, galaxies, and clusters. Today, while expansion continues, gravity shapes the formation of cosmic structures, maintaining local order amidst universal growth. Understanding gravity's role in the expanding universe helps scientists predict the cosmos's future. Whether expansion will continue forever, slow, or even reverse, gravity is the cosmic counterweight, subtly controlling the pace of the universe. Fact 59. The cosmic web, gravity's grand design. Gravity has a grand design on the largest scales, the cosmic web. Galaxies are not scattered randomly but form filaments, sheets, and voids, shaped by gravity acting over billions of years. Dark matter plays a key role, providing the scaffolding upon which galaxies grow. The web is a complex network. Dense nodes host galaxy clusters, while long filaments connect them and vast voids stretch between. Gravity pulls matter along these filaments, forming streams of galaxies and fueling the growth of superclusters. The cosmic web is a reminder that gravity isn't just local. It orchestrates the universe's architecture on a scale beyond imagination. It's the invisible skeleton holding together billions of galaxies, guiding their motion and shaping the universe itself. Fact 60. Could the universe collapse again? Gravity may one day have the final word. If the universe contains enough matter, gravity could eventually halt the expansion and reverse it, leading to a big crunch. Galaxies, stars, and planets would collapse toward each other, undoing billions of years of cosmic growth. Whether this will happen depends on the balance between gravity and dark energy. Observations suggest that dark energy currently dominates, driving acceleration. But in theory, changes in cosmic conditions could tip the scales, allowing gravity to reclaim the universe. This possibility shows that gravity is not only a local force shaping stars and galaxies, but also a cosmic player influencing the ultimate fate of everything. It's the silent architect that could one day rewrite the universe's story. Fact 61. Galileo's Leaning Tower Experiment. Galileo Galilei was curious about a question that had puzzled thinkers for centuries. Do heavier objects fall faster than lighter ones? Legend has it that he climbed the Leaning Tower of Pisa and dropped two spheres of different masses to see what would happen. To everyone's surprise, the balls hit the ground at nearly the same time. Galileo's insight shattered the long-held belief from Aristotle that weight determined falling speed. Gravity, it turned out, accelerates all objects equally, regardless of mass, ignoring air resistance, of course. This experiment laid the groundwork for modern physics. It was a simple act, yet its implications were profound. It demonstrated that gravity operates universally, and it introduced the concept of acceleration independent of weight. Galileo's work showed that careful observation could reveal nature's hidden rules, even when they contradict intuition. The Leaning Tower experiment reminds us that gravity is predictable, measurable, and consistent, qualities that allowed Newton and others to formalize the laws governing motion and gravitational pull. Fact 62. The Cavendish experiment. Measuring G-gravity pulls everything, but how strong is it exactly? In 1898, Henry Cavendish devised an ingenious experiment to measure the gravitational constant, G, a fundamental value that quantifies the strength of gravity. He used a torsion balance, a horizontal bar suspended by a thin wire with lead spheres at each end. Nearby, larger lead spheres were positioned to attract the smaller ones. The tiny twisting of the wire revealed the gravitational pull between the masses. From this, Cavendish could calculate both G and, surprisingly, Earth's mass. The experiment was delicate. The forces were minuscule, and the slightest vibration could ruin the measurement. Yet Cavendish's careful work gave humanity the first accurate measurement of gravity's absolute strength. His experiment confirmed that gravity is universal, predictable, and measurable, even in a laboratory setting. It's a reminder that gravity, though invisible and pervasive, can be quantified with clever design, opening the door to precise physics calculations that underpin everything from orbits to space travel. Fact 63. Gravity probe B and curving spacetime. Einstein's theory of general relativity predicts that massive objects like Earth warp spacetime, twisting it as they rotate. To test this, NASA launched Gravity Probe B in 2004, carrying ultra-precise gyroscopes into orbit. The gyroscopes measured tiny changes in their spin direction, caused by the curvature of spacetime and the frame-dragging effect of Earth's rotation. The results confirmed Einstein's predictions to remarkable precision. Gravity Probe B shows that gravity is more than just a pull. It's a curvature of the very fabric of the universe. Objects move along these curves, following the natural paths dictated by mass and rotation. It transformed our understanding from Newton's force view to Einstein's geometric interpretation, showing that gravity shapes space and time itself. Fact 64. Freefall experiments in space is the ultimate laboratory for studying gravity, or the near absence of it. Astronauts aboard the International Space Station experience freefall, orbiting Earth at high speed. In this microgravity environment, objects float, yet gravity is still at work, keeping the station in orbit. Freefall experiments reveal how fluids, flames, and biological systems behave without the constant tug of gravity. They test theories, improve medical understanding, and help design spacecraft. By simulating weightlessness, scientists can isolate gravity's effects and better understand its fundamental role in shaping matter and motion. Freefall demonstrates that gravity isn't just about weight. It's a framework that governs motion, even when it seems absent. It's everywhere, quietly orchestrating the dance of objects in orbit. Fact 65. LIGO and the detection of gravitational waves. Gravity doesn't just pull, it ripples through space-time. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected these waves for the first time, confirming a century-old prediction by Einstein. Gravitational waves are caused by massive accelerating objects like merging black holes. LIGO measures tiny distortions in space-time, smaller than a fraction of a proton's width, caused by waves passing through Earth. Each detection reveals details about cosmic collisions billions of light-years away, offering a new way to hear the universe. This discovery transformed astronomy. We now have a sense of gravity not just as a force acting on matter, but as a dynamic fabric that vibrates, carries energy, and tells the story of the universe's most violent events. LIGO allows us to explore realms previously invisible, turning Einstein's theory into observable reality. Fact 66. How the International Space Station uses microgravity. The International Space Station, ISS, isn't free of gravity, but it experiences microgravity, a near weightless state caused by its continuous free fall around Earth. Astronauts and experiments aboard the station float effortlessly, allowing scientists to study the subtle effects of gravity on physical and biological systems. Microgravity has transformative effects. Fluids form perfect spheres, flames behave differently, and cells grow in 3 dimensions instead of layers. These conditions provide insights impossible to achieve on Earth, from better drug development to understanding bone and muscle loss in astronauts. Even in orbit, gravity is still present. It keeps the ISS in a stable orbit around Earth. The station's motion creates the illusion of weightlessness, a reminder that gravity is always at work, shaping movement and behavior, even when it seems absent. Microgravity is a unique laboratory, revealing how deeply gravity influences every process we often take for granted. Fact 67. Simulating gravity on Earth. What if we could replicate gravity without leaving the planet? Engineers and scientists have developed clever ways to simulate gravity for training and research. Rotating centrifuges, for instance, spin humans or objects to create artificial gravity through centrifugal force. This is crucial for astronaut training, especially for long missions where prolonged microgravity affects the body. Simulating gravity helps maintain muscle strength, cardiovascular health, and coordination. It also allows scientists to study how biological systems respond to different gravitational conditions without leaving Earth. Gravity simulation reminds us that, even when we try to escape its effects, this invisible force governs motion and physiology. By creatively mimicking it, we gain a deeper appreciation for how integral gravity is to life in the universe. Fact 68. Drop towers and parabolic flights. Scientists use drop towers and parabolic flights to study short periods of microgravity. In drop towers, experiments are dropped in a vacuum chamber, free-falling for several seconds, allowing researchers to observe behavior in near-weightless conditions. Parabolic flights, often called vomit comets, use specially flown aircraft that follow a parabolic trajectory. For brief moments at the top of the arc, objects and passengers experience microgravity. These methods provide valuable data for physics, biology, and material science, all while remaining on Earth. These experiments show that even small windows of altered gravity can yield profound insights. Gravity, normally constant, becomes a variable, helping us understand its influence and prepare for life in orbit or beyond. Fact 69. The atomic clock and gravitational time. Dilation gravity doesn't just pull matter, it affects time itself. Atomic clocks, which measure time with extraordinary precision, have confirmed that clocks tick slower in stronger gravitational fields. This effect, predicted by Einstein's general relativity, is called gravitational time dilation. Even the difference between a clock on a mountaintop and one at sea level is measurable. Satellites in orbit experience weaker gravity and must account for faster ticking to ensure GPS accuracy. Gravity subtly warps time everywhere, and atomic clocks are our tools to measure this invisible distortion. This phenomenon reminds us that gravity isn't just about falling objects, it bends the very fabric of space-time, connecting motion, mass, and time in ways that are both profound and measurable. Fact 70. Quantum tests of gravity. Gravity meets the quantum world in fascinating ways. Scientists are conducting experiments to see how gravity affects particles at the smallest scales, using ultra-cold atoms, interferometry, and quantum sensors. These tests probe whether quantum mechanics and gravity can coexist within a single framework. Tiny deviations or unexpected behaviors could hint at new physics, helping us reconcile Einstein's general relativity with quantum theory. Quantum tests of gravity show that this force isn't just a cosmic player, it acts on the smallest scales too. By studying it in the quantum realm, we explore the fundamental rules that govern the universe, from the tiniest particles to the largest galaxies. Fact 71. How gravity shapes our bones and muscles. Gravity does more than make things fall. It literally shapes our bodies. Every step we take, every movement we make, our bones and muscles work against gravity's pull. This constant resistance keeps our skeletons strong and our muscles toned. The cells in our bones, called osteocytes, sense mechanical stress from gravity and stimulate bone growth accordingly. Muscles respond in kind, contracting and adapting to keep us upright and mobile. Without gravity's gentle but persistent tug, our bodies would weaken over time. From an evolutionary perspective, gravity has been a sculptor. Walking on two legs, running, lifting, and carrying, every activity that defines humans has been shaped by the need to resist the pull of the Earth. Our bodies are built to thrive in a world where gravity is a constant companion. Fact 72. Why astronauts lose bone density space travel is one of humanity's most thrilling achievements, yet it comes with challenges that go far beyond the excitement of floating above Earth. One of the most significant physiological effects of long-term spaceflight is the loss of bone density. On our planet, gravity constantly works on our bodies, giving bones a reason to stay strong and muscles a reason to stay active. In microgravity, however, this invisible force essentially disappears, and the consequences are profound. In orbit, astronauts experience weightlessness. Their bodies no longer have to support themselves against the pull of gravity. Bones that once bore the weight of walking, running, and standing suddenly find themselves unburdened. This lack of mechanical stress triggers a process called bone resorption, where the body breaks down bone tissue faster than it can rebuild it. Over the course of a long mission, astronauts can lose up to 20% of their bone mass, particularly in the spine, hips, and legs, the areas that normally bear the brunt of Earth's gravity. Muscles aren't immune either. With less resistance to movement, muscles atrophy, shrink, and weaken. Tendons and ligaments lose some of their strength, making the body more vulnerable to injury. These changes are reversible to an extent, but they illustrate just how crucial gravity is in maintaining the structural integrity of our bodies. To combat these effects, astronauts rely on rigorous daily exercise. Special resistance machines, harnesses, and treadmills are designed to simulate the weight-bearing experience of Earth. Exercises such as squats, running, and weightlifting in space help maintain bone density and muscle strength. Nutrition also plays a critical role. Adequate intake of calcium, vitamin D, and other nutrients supports the ongoing maintenance and repair of bones, even when gravity is absent. Studying bone loss in space not only helps protect astronauts on long-duration missions, but also offers insights into similar conditions on Earth. Osteoporosis, a disease in which bones become weak and brittle, shares some characteristics with the bone degradation seen in microgravity. Understanding how bones respond to the absence of gravity helps researchers develop better treatments and preventive measures for those affected by bone loss on Earth. Ultimately, the phenomenon of bone density loss in space highlights gravity's subtle, yet powerful influence on our physiology. On Earth, we take for granted that our skeletons remain strong, our muscles toned, and our bodies supported. In the absence of gravity, these systems quickly reveal their dependence on the constant pull we normally never think about. Space shows us, in a literal sense, how much of our very structure is designed for a planet with gravity, a reminder of how intricately life is tied to the invisible force that keeps us grounded. Fact 73. The sense of balance and gravity. Our sense of balance relies entirely on gravity. Inside the inner ear, the vestibular system detects the position of our head relative to the pull of the Earth. Tiny structures called otoliths shift as we move, sending signals to the brain about orientation and motion. Without gravity, this system can become confused. Astronauts floating in space may feel disoriented, and everyday tasks like walking or standing can become challenging upon returning to Earth. Even subtle head tilts or sudden movements rely on gravity to keep our bodies coordinated. Balance is a silent partnership with gravity. Every step, every adjustment we make to stay upright depends on our body constantly interpreting the pull of the Earth. It's a reminder that gravity is not just external, it's deeply intertwined with our perception and coordination. Fact 74. How gravity affects blood flow. Gravity shapes the movement of fluids in our bodies, including blood. On Earth, it pulls blood toward our lower extremities, and the heart works continuously to pump it back up to the brain. Without gravity, blood redistributes toward the head, causing puffiness in the face and sometimes pressure in the eyes. Astronauts experience this fluid shift in space, leading to facial swelling and changes in cardiovascular function. The body adapts over time, but returning to Earth can be a challenge as gravity suddenly demands normal circulation again. Blood flow is a dynamic dance with gravity, highlighting how even tiny pulls influence every beat of the heart, the delivery of oxygen, and the proper function of organs. Fact 75. The challenge of living in microgravity. Life in microgravity is exciting but demanding. Floating objects, altered sleep cycles, weakened bones, and fluid shifts all make simple tasks challenging. Even eating and drinking require adjustments, as liquids behave unpredictably in weightlessness. Astronauts rely on specialized equipment, exercise routines, and careful planning to maintain health and safety. Microgravity reveals the deep connection between humans and Earth's gravity, showing how our bodies, behaviors, and technologies have evolved to live under its constant influence. Living in space is a lesson in adaptation. It reminds us that gravity is not just a force, it is a foundation for life as we know it, shaping our biology, behavior, and daily routines. Fact 76. Artificial gravity in space. Habitats. Living in space is exciting, but microgravity comes with challenges, from muscle loss to bone density decline. To counter these effects, scientists and engineers explore artificial gravity. One common method is rotation. Spinning a space habitat creates centrifugal force, which acts like gravity, pushing objects and people toward the outer edge. Imagine a giant spinning wheel in space. Astronauts walk along the rim as if on Earth, experiencing a simulated pull. The faster the spin, the stronger the artificial gravity. Designing such habitats requires careful calculations. Too fast, and the rotation can cause dizziness or nausea. Too slow, and the effect isn't strong enough. Artificial gravity could allow long-term space missions like trips to Mars or permanent colonies in orbit to support healthy human life. It shows how gravity isn't just a natural force. We can mimic its effects to maintain life, proving how deeply humans depend on this invisible pull. Fact 77. How babies develop under gravity. Gravity isn't just important for adults. It affects development from the very beginning of life. In the womb, the fetus experiences a combination of maternal movement and gravity. This gentle pull helps bones, muscles, and joints develop strength and orientation. Studies of astronauts in space show that microgravity could influence how skeletal structures form. Without gravity, bones may grow differently, muscles may weaken, and the vestibular system, responsible for balance, might not develop the same way. This suggests that life on Earth is profoundly adapted to the consistent pull of gravity. Gravity's influence on early development reminds us that this force is a silent teacher, shaping the foundations of life itself. From the first movements in the womb to the growth of the musculoskeletal system, gravity guides our bodies even before birth. Fact 78. Gravity and aging. Is there a connection? Gravity affects us throughout life. Over decades, its constant pull contributes to posture changes, spinal compression, and joint wear. Bones lose density, muscles weaken, and fluids redistribute, subtly influencing how we age. Interestingly, astronauts experience accelerated aspects of these changes in microgravity. Bones and muscles deteriorate faster without gravity's resistance, while the heart adapts to a new circulation pattern. Upon returning to Earth, the body must readjust to the persistent pull. These observations suggest that gravity plays a role in aging, both as a force that strengthens us and as a factor contributing to wear over time. Life in Earth's gravity is a continuous balance, sculpting our bodies while subtly testing them as we grow older. Fact 79. The long-term health effects of low gravity. Extended exposure to low gravity brings a host of physiological challenges. Astronauts experience muscle atrophy, bone loss, fluid redistribution, and changes in cardiovascular function. Vision can be affected due to increased pressure in the eyes, and balance may suffer when returning to Earth. Researchers simulate these effects on Earth using bed rest studies, parabolic flights, and water immersion. Understanding these changes is crucial for planning long-term missions to the Moon, Mars, or beyond. Low gravity tests human resilience and highlights just how deeply Earth's pull has shaped our bodies. Despite these challenges, the human body shows remarkable adaptability. With exercise, nutrition, and careful planning, astronauts maintain health, demonstrating that while gravity is essential, we can survive, and even thrive, in altered conditions. Fact 80. Can humans adapt to other gravity levels? Could humans live on Mars or the Moon, where gravity is weaker than Earth's? Adaptation would be possible, but the body would undergo changes. Bones might become less dense, muscles weaker, and the cardiovascular system would adjust to lower pressure. Growth and development could also be affected in children born under these conditions. Technology, like exercise devices, artificial gravity, and tailored nutrition, could help mitigate these effects. However, full adaptation would likely take generations. Life under different gravity would require humans to evolve or engineer solutions, blending biology with ingenuity. This exploration shows that gravity isn't just a background force, it's a shaping factor for life. Changing it requires careful consideration, planning, and an understanding of just how deeply this invisible force molds our bodies, health, and survival. Fact 81. How gravity powers hydrodams. Gravity isn't just a cosmic force, it's a source of energy we use every day. Hydroelectric dams harness the pull of water falling from a height to generate electricity. Water stored in a reservoir has potential energy due to gravity. When released, it accelerates downward, spinning turbines and producing power. This simple principle powers millions of homes worldwide. Gravity does the heavy lifting while engineers focus on directing and controlling the flow. It's a reminder that even a force we can't see directly can be converted into tangible benefits, powering cities and industries. Hydroelectric systems also illustrate the careful balance with nature. Engineers must account for water pressure, gravity's pull, and structural stability to safely and efficiently generate energy. In this way, gravity is both a provider and a challenge, shaping human innovation as much as it shapes the world. Fact 82. Using gravity in architecture and bridges. Gravity shapes more than rivers. It governs buildings, bridges, and human engineering. Architects and engineers design structures with gravity in mind, ensuring weight is distributed safely to prevent collapse. Arches, domes, and suspension bridges all rely on gravity to function effectively. An arch, for example, channels weight down and outward, letting gravity do the work of keeping the structure standing. Suspension bridges balance forces, with gravity pulling the deck downward, while cables redirect the load to towers. Without understanding gravity, none of these feats would be possible. By respecting gravity's pull, humans have built monuments, skyscrapers, and bridges that stand for centuries. It's a reminder that this invisible force isn't just an obstacle, it's a partner in human design, quietly ensuring stability in structures that define our civilization. Fact 83. Gravity-assisted launch systems. In space exploration, gravity can be an ally. Gravity-assisted launches, or slingshots, use the pull of planets to increase spacecraft speed. By flying close to a planet, a spacecraft can gain momentum without using additional fuel, redirecting its trajectory to reach distant targets. This technique has been crucial for missions to the outer planets and beyond. Spacecraft like Voyager and Cassini used gravity assist to travel vast distances efficiently. Engineers carefully calculate the angles, speeds, and planetary positions to make these maneuvers work. Gravity-assisted launches show that gravity isn't just a force to overcome, it's a tool. By understanding and harnessing its pull, humanity can explore the solar system more efficiently, using the universe's natural forces to our advantage. Fact 84. Gravitational sensors and geophysics. Gravity helps us explore Earth itself. Gravitational sensors detect tiny variations in the pull of gravity caused by differences in mass below the surface. These measurements reveal underground structures, mineral deposits, and hidden geological features. Geophysicists use these tools to study earthquakes, volcanic activity, and even groundwater flow. Gravity mapping has become essential in understanding our planet, from predicting natural disasters to discovering resources without digging or drilling. This application highlights how gravity isn't just a universal force, it's also a practical tool, allowing humans to explore both the cosmos and the hidden depths of Earth. It's an invisible guide, pointing the way to discoveries beneath our feet. Fact 85. Spacecraft navigation and gravitational pulls. Navigating spacecraft requires careful accounting for gravity. Every planet, moon, and massive object exerts a pull, influencing a spacecraft's path. Mission planners must calculate trajectories precisely to ensure spacecraft reach their targets safely and efficiently. Gravity can speed up, slow down, or redirect a spacecraft. Even small gravitational influences from asteroids or distant planets can alter courses over time. Using gravity wisely, engineers design paths that minimize fuel consumption and maximize mission success. This shows that gravity is not just an obstacle in space, it's an invisible partner guiding travel across the solar system. Understanding its pull is essential for every mission, from satellite launches to interplanetary exploration. Fact 86. How gravity helps. Map underground resources. Gravity isn't just a cosmic force, it's a detective tool for exploring the Earth. Subtle variations in gravity can reveal hidden features beneath the surface, such as mineral deposits, oil reservoirs, or ancient cavities. Geophysicists use gravimeters to measure these tiny differences. Denser materials, like metal ores, exert a slightly stronger pull, while less dense regions, like caverns, create weaker signals. By mapping these variations, scientists can create detailed underground maps without digging. This technique saves time, money, and the environment, showing that gravity can be a guide, pointing us toward resources hidden from plain sight. It's invisible, yet its effects can reveal the unseen architecture of our planet. Fact 87. The role of gravity in clocks and pendulums. Gravity is a silent timekeeper. Pendulum clocks rely on it to regulate motion. A swinging pendulum moves in response to gravity, creating a consistent rhythm that drives the clock mechanism. Even a small change in gravitational pull, like moving to a higher altitude, can slightly alter the pendulum's swing and the clock's accuracy. Atomic clocks take this concept further. Gravitational time dilation, predicted by Einstein, shows that clocks tick slower in stronger gravity. GPS satellites must account for this effect to provide accurate positioning. Gravity shapes our perception of time, turning a universal force into a precise measure of seconds, minutes, and hours. It reminds us that even the passage of time is intertwined with this invisible pull. Fact 88. Gravity batteries. Storing energy with weight. Gravity isn't just a force to overcome, it can store energy. Gravity batteries use heavy weights lifted to a height to store potential energy. When energy is needed, the weights descend, turning generators to produce electricity. These systems are clean, efficient, and sustainable. Unlike chemical batteries, they rely on simple physics rather than materials that degrade over time. Gravity provides a reliable, predictable source of stored energy, proving that even the oldest force in the universe can power modern technology. Gravity batteries illustrate how engineers harness natural forces creatively. By lifting and dropping weights, we can tap into energy that's already part of our environment, making gravity a partner in sustainable energy solutions. Fact 89. How gravity influences aviation. Gravity is a constant factor in aviation. Airplanes must generate lift to counteract the pull of gravity, balancing thrust, drag, and weight to maintain controlled flight. Pilots account for gravity during takeoff, maneuvering, and landing. Even small changes in gravity, like flying at different altitudes, affect fuel consumption, speed, and handling. Weather phenomena, turbulence, and thermals interact with gravity, making it essential for flight planning. Without gravity, aviation as we know it wouldn't exist. It shapes the skies, determining the forces airplanes must overcome and giving structure to the very act of flying. Gravity is both a challenge and a guide in aviation, influencing every flight path. Fact 90. The science of gravitational lensing in telescopes. Gravity can bend light. When light passes near a massive object like a galaxy or black hole, gravity warps the space around it, bending the light's path. This effect, called gravitational lensing, allows astronomers to see objects that would otherwise be hidden. Telescopes use gravitational lenses to magnify distant galaxies, study dark matter, and even detect exoplanets. This natural cosmic telescope turns massive objects into tools for observing the universe. Gravitational lensing shows that gravity isn't just a pull, it's a lens through which we can explore the cosmos. It bends light, warps space, and helps us uncover the universe's most distant and mysterious objects. Fact 91. Could we control gravity one day? The idea of controlling gravity has fascinated humans for centuries. Imagine hovering vehicles, floating buildings, or launching spacecraft without rockets. While it sounds like science fiction, scientists are exploring the boundaries of gravity control. Currently, we can't switch gravity on or off, but we can manipulate its effects. Magnetic levitation and centrifugal force can simulate or counteract gravity in specific situations. Experiments in labs and space habitats help us understand how gravity interacts with matter and energy. If future technologies could harness or modify gravity directly, it would revolutionize transportation, energy, and space travel. While it's far from reality, the question pushes us to explore deeper, test limits, and rethink how this fundamental force governs everything around us. Gravity for now remains untouchable, but curiosity drives us toward the day we might control it. Fact 92. Anti-gravity. Theories and sci-fi inspirations. Anti-gravity has long fueled the imagination of writers and inventors. From floating cars in movies to spacecraft hovering above alien landscapes, fiction often depicts a world where gravity can be negated at will. In science, anti-gravity explores theoretical ways to counteract gravitational pull. Ideas include manipulating exotic matter, electromagnetic fields, or negative energy. None have been achieved yet, but they inspire real-world research. Concepts that once seemed impossible, like flight or space travel, were once just science fiction, and now they are everyday realities. Anti-gravity may remain a dream, but these theories demonstrate how human curiosity blends imagination with physics. Exploring impossible ideas often leads to real scientific breakthroughs, even if we never completely defy gravity. Fact 93. Quantum gravity, the next great mystery. Gravity governs galaxies and falling apples alike, but reconciling it with quantum mechanics is one of physics' biggest challenges. Quantum gravity seeks to explain how gravity behaves on the tiniest scales, where particles and forces interact in ways Einstein's equations don't describe. This field attempts to merge general relativity with quantum theory. Researchers explore black holes, the early universe, and hypothetical particles to uncover how gravity works at its most fundamental level. Understanding quantum gravity could answer questions about the origin of the universe, the nature of space-time, and even the behavior of matter under extreme conditions. It's a mystery at the heart of physics, reminding us that gravity is not just familiar, it's profound, complex, and still largely unexplored. Fact 94. String theory's view of gravity. String theory offers a radical view of gravity. Instead of seeing particles as points, it models them as tiny vibrating strings. According to this theory, gravity emerges naturally from one of these strings' vibrational patterns, possibly explaining its unique strength and behavior compared to other forces. If correct, string theory could unify gravity with electromagnetism, weak and strong nuclear forces, achieving the long-sought theory of everything. Gravity in this view is woven into the very fabric of the universe, not just a pull between masses. Though still theoretical, string theory reshapes how scientists think about gravity. It's a reminder that even the most familiar force might be more intricate than we can imagine. Fact 95. The search for gravitons. The gravity particle. Physicists wonder, does gravity have a particle? Enter the graviton, a hypothetical particle that mediates gravitational force, much like photons carry electromagnetic force. Detecting gravitons would be revolutionary, revealing gravity's quantum nature. Experiments face extreme challenges. Gravity is incredibly weak compared to other forces, making its particle elusive. Yet theoretical models and indirect evidence guide the search. Discovering gravitons could bridge the gap between general relativity and quantum mechanics, completing our understanding of fundamental forces. The hunt for gravitons reminds us that gravity, though ever-present, still holds secrets. It's not just the force that keeps us grounded. It might be the key to understanding the universe's most profound mysteries. Fact 96. Gravity and the multiverse idea. Some of the most mind-bending theories in physics involve gravity and the multiverse. Could our universe be just one of many, each with its own laws? Gravity plays a key role in these ideas. In some multiverse models, variations in gravity's strength could determine whether a universe can form stars, planets, or even life. Too weak, and matter would never coalesce. Too strong, and everything would collapse quickly. Gravity, in essence, might be the force that decides which universes can exist. Studying gravity in extreme conditions gives scientists clues about how other universes, if they exist, might behave. It's a reminder that gravity isn't just local. It could shape realities far beyond our own, making it one of the most influential forces in the cosmos. Fact 97. Experiments in extra dimensions. Gravity might also hide secrets in extra dimensions. Some theories, like string theory, suggest that gravity leaks into higher dimensions, which could explain why it is much weaker than other fundamental forces. Physicists test these ideas with particle accelerators, sensitive measurements, and experiments detecting tiny deviations in gravity at microscopic scales. If true, extra dimensions could reveal new physics and even possibilities for future technologies. Exploring gravity beyond 3 dimensions shows that the universe is more mysterious than we realize. What we feel as a constant pull might be just the tip of a far deeper, multi-dimensional story. Fact 98. The role of gravity in time travel. Theories. Gravity doesn't just move objects, it bends time. According to general relativity, strong gravitational fields slow the passage of time. This principle has inspired countless time travel theories, from black hole voyages to wormholes. Near a massive object, time dilation becomes extreme. In theory, someone could experience minutes while years pass elsewhere. While practical time travel remains science fiction, these gravitational effects are real and measurable, proving that gravity and time are intertwined. Gravity teaches us that time is flexible, not absolute. It hints at possibilities once thought impossible, showing that even everyday forces can open doors to extraordinary concepts. Fact 99. Gravity and the fate of the universe. The ultimate fate of the universe is a cosmic tug-of-war between gravity and expansion. Gravity pulls matter together, while dark energy pushes galaxies apart. The balance between these forces will determine whether the universe keeps expanding, slows, or collapses in a big crunch. Observations suggest expansion is accelerating, meaning gravity may never fully overcome the pull of dark energy. Yet gravity still governs the structure of galaxies, stars, and clusters. It's the invisible architect shaping both the present and the potential futures of the cosmos. Understanding gravity is key to predicting how the universe will evolve. It's a force with a say in the ultimate story of everything we know. Fact 100. What gravity still hasn't told us. Even after centuries of study, gravity holds secrets. We don't fully understand dark matter and dark energy, which together dominate the cosmos. Quantum gravity remains elusive, and unifying it with other fundamental forces is one of science's greatest challenges. Gravity influences everything from falling apples to colliding galaxies, yet it still surprises us. Could there be particles we haven't discovered, dimensions we can't detect, or phenomena beyond imagination? The story of gravity is ongoing. Each discovery opens new questions, reminding us that this invisible force is not just a pull, it's a guide, a teacher, and a mystery that continues to shape the universe and our quest to understand it.